This is a brief part 2 to my lecture on the electric force. I'm going to do a specific example. Okay, as is always the case, copy down that example into your notes prior to me then posting the solution here on the board. You can find the lecture example on a document in the folder called lecture example, so pause the film right now and go ahead and copy that example down into your notes. As is always the case, however, I've cast it up here into my screen. Let me now read it to you as I begin to work my way through the problem. All right, so two charges are placed 5 centimeters apart and they're fixed in place. This then means that the charges are nailed in place, they can't move. So let's say that right here is the first charge, we'll call it Q1. Here's the second charge, Q2, and they're separated by a distance here, R, that's given to us as 0.05 meters. So notice immediately that I've already converted here the centimeters into meters by dividing by 100. Okay, and then the value of the charges themselves are as follows. We're given them as both as positive values, and they're in terms of what are called microcoulombs. Micro refers to 10 to the minus 6. When you're talking about the charges placed on my plastic and glass rods, for example, in my short lecture demonstration video from earlier, typically the amount of charge that is present there in those situations is in terms of microcoulombs, millionths of coulombs. So in this particular problem, we're given that Q1, for example, is equal to positive 3 times 10 to the minus 6 coulombs. Once again, micro is 10 to the minus 6. Okay, and then the other charge, Q2, is also positive. That's given to us as 5 times 10 to the minus 6 coulombs. Once again, it's 5 microcoulombs. Now, because both of these charges are positive, this then means that they would both exert an electrostatic force of repulsion on one another. So, for example, in this direction right here, there is a force on Q2 due to Q1. However, immediately Newton's third law comes into play. If you think of this force right here as the action, then the reaction is that there's an equal amount of force on Q1 due to Q2. Once again, equal and opposite reaction forces here. That's Newton's third law. Suffice it to say the two charges repel each other. Okay, so we're going to determine the value of the force that one charge exerts upon the other in part A of the example. And it doesn't matter which of these forces we choose here because by Newton's third law, they're the same thing. All right, so in order to calculate that force, we're going to use Coulomb's law, which is the following expression, and recall the fundamental constant K. The fundamental constant K is 9 times 10 to the 9th Newton meter squared per Coulomb squared. So let's just go ahead and calculate this out. All right, so just plugging everything into my calculator here, I first of all have K, and then multiply by the two charges, so times 3 times 10 to the minus 6, times 5 times 10 to the minus 6, and then I divide then by the distance squared. So if I divide by 0.05 squared, this ends up being then 54, and we're talking about force here, so then therefore it's in terms of newtons. Okay, and now in part B, we're going to double the distance between the two objects, and then eventually in part C, we'll triple the distance between the two objects. So take a look at part B first. So now we're going to double the distance, so then therefore 2r here, that's equal to 0.10 meters, like so. But here's an easy way to work our way through this portion of the example. Okay, now the force is going to be K, Q1, Q2 divided by quantity 2r squared, like so. 2 squared, however, is 4. Pull that out in front like so, and then you end up with a value of the force here that is 1/4 of the original value. Remember that this quantity right here we just found is 54 newtons, so then therefore the value of the force is 1/4 of that value. So just 54 divided by 4, and that comes out to be 13.5 newtons, like so. And then lastly, in part C of the problem, now we'll just triple the distance between the charges. So now the distance is 3r, okay, so that's equal to 0.15 meters numerically. But once again, we can shortcut this problem in the following way. Now the force is going to be K, Q1, Q2 divided by quantity 3r squared, like so. 3 squared is 9. So pull that 9 out in front, like so. And now the value of the force is going to be 1/9 of the original value. Once again, the original value was 54 newtons. So now I'm just going to take 54 and divide that by 9, and that comes out to be 6 newtons. Like so. So like the force of gravity, the electric force also obeys an inverse square law. Okay, based upon this problem and the lecture material here, you could actually go ahead and start the next problem set as well. I've posted that in the folder on Schoology. I'll set a due date for that problem set, however, a little bit later on. As of now, you could actually work on the first 2 problems from that problem set. Thank you. Today's shirt, by the way, is Skeleton Witch.